So let's do an example kind of similar to the first one that we did today, but in some respects quite different. Let's do a trigonometric integral. Let's do the integral of the sine of 7x. So again, it's a case of linear composition. I've replaced the x that's in our common integral with a linear function, but because the constant term, the plus b, didn't seem to do anything in the first example, this time I've just gone with something of the form m times x. So just 7x as opposed to 7x plus 5 or 7x minus a half. And we could always come back and look at another one of those types of examples later if we feel that we need to. So again, we're going to hope that the result of this integral is something similar to the corresponding common integral, where we know that the integral of sine x is negative cosine x plus c. And so again, let's take a similar guess to the one that we made last time, even though we're probably going to get the sense from that first example that this isn't going to be quite correct. Let's assume again that this is going to follow exactly the same pattern. That the integral of the sine of 7x is just negative cosine of 7x plus c. And again, we're going to check that that's right by differentiating it. Well, again, we're going to need the chain rule because that's the derivative of a composite function now. I should actually write down my little prime symbol. And so the derivative of cosine we know is negative sine. So the negative will just give us a positive sine of 7x. But then by the chain rule, we have to multiply that by the derivative of the inside function. The derivative of 7x, of course, is 7. And then the plus c again. That just differentiates away to 0. So it is pretty similar to the previous example. We don't get back our original integrand. We don't get back sine of 7x, but we get back 7 times sine of 7x. So again, it's that coefficient of x that seems to matter. And we can imagine if we did have 7x plus or minus a constant here, almost nothing would have changed. Because in particular, again, when we check by the chain rule here, if our guess had been, say, negative cosine of 7x plus a half, well, when we differentiate that inside function, 7x plus a half, we still just would have gotten 7 here. So it really does seem to be that coefficient of x that's important, not the linear term, or not the constant term, rather, in our linear composition. And so, while again that tells us that our guess is wrong, we can conclude that the integral then of 7 times 7x, that is negative cosine of 7x plus c. And then we can do exactly what we did in the previous example. We could factor out that 7 and divide it across. So the thing that we're after, sine of 7x, that's going to be negative 1 over 7 cosine of 7x plus c. So in both of these cases, our guess based on the common integral was almost right, but we had to divide by that coefficient of x from our linear composition. In the first example, we had to include an extra division by 2. In this case, we had to include an extra division by 7. And in fact, that's always going to be true, because if we just follow the pattern of our common integrals, as we've been doing here, when we go to check, we're always going to wind up applying the chain rule and wind up with whatever m is in our linear function mx plus b as an extra coefficient. It's a constant, though, so we can adjust for that by dividing our original guess by m, which therefore gives us the following result. If little f of x is a function with antiderivative capital F of x then the integral of little f of mx plus b, so the integral of a linear composition of that function little f of x, well, it's almost capital F of x. It's capital F of mx plus b, but we have to account for that m. So we divide whatever that expression is by the constant m, and of course, we remember to add on our constant of integration. And for linear composition, that will always work. So we don't need to go through this process of guessing and checking and adjusting. If we've got a common integral, but with a linear composition, now we know the pattern. So for example, suppose I wanted to work out the integral of, let's say, 1 over 2 minus x to the 6th. Well, that's an example of a linear composition, because we could compare that to just the integral of 1 over x to the 6th, which you might find useful if you rewrite that as a proper power. And that's the integral of x to the negative 6. There we can just use the power rule. So we can add 1 to the power to get x to the negative 5, divide by the new power. So what this result tells us is that this integral will follow the exact same pattern, but we have to account for the coefficient of the x. So we're going to come over to what we would have gotten from the common integral. We'll replace the x with that linear function. So we'll get 2 minus x all to the power of negative 5. We'll divide by negative 5 because that's what the common integral tells us that we have to do, but we're also going to divide by the coefficient of x, which in this case is negative 1. And of course, tack on that plus c. So then that's going to give us, well, negative 5 times negative 1 is positive 5. So we could write it as 1/5 times 2 minus x to the negative 5 plus c. Or you could turn that back into a fraction, or you could write it as 1 over 5 times 2 minus x all to the 5th plus c. Either one is fine. And so that would be correct, and we could check that that's correct by differentiating it. And so we've mostly used our result from the common integrals, but we've adjusted, we've compensated for the coefficient of x, which in this case is the negative 1. We've divided by that as well. As long as you do that, instances of linear composition with those common integrals is actually pretty straightforward. We'll do some more on this in the next video.